Hello, my name is Lewis Crabtree. In this video, I will be discussing my solution to the pathfinding problem using the grass-fire pathing algorithm. To get started, I will show a quick demo of the program, and then we can open up the code and I'll provide a brief overview of my solution. This is the main entry point of the program where it asks us to enter the size of the grid, at least 8 by 8. For this demo, we will use 9 by 9. It then prints out the grid for us to see. This grid represents the search space of the pathfinding problem. Right now it is empty, so we'll add some obstacles to it. We can enter a number between 10 and 20%. We'll use 20%. And we can see that the grid now has some obstacles in it, represented by X's in the cells. We can choose a column number for the starting node, which will be in the first row of the grid. For this demo, we will use column 1. It is 0 based, so we see that our starting node is in row 0, column 1. We can now enter a row for the destination cell on the bottom half of the grid between 4 and 8. For this demo, we will use 8. And we can now enter a column number. We'll use column 6. We can see that our starting node is here, our destination node is here, and we have X's representing the blocked cells, or the obstacles. We can now press enter to find distances from the destination node. And we see that the cells now have numbers in them representing the distance from the destination node. We can press enter again to display all of the best paths that the grass-fire algorithm finds. We can see here that we have found 9 unique solutions for this grid. They have been printed above. Alright, let's jump over to the code. Alright, this is the main method of the program. First we print our welcome message, we then get our grid size from the user input, generate our obstacles, get the starting cell, the destination cell, and then do our discovery, where we indicate the distances of each node, and then the pathing, where we use those distances to find all possible shortest paths. We'll start with generating our actual grid. We create a 2D array with a cell object, which contains fields for distance and state. The possible states here are open, blocked when there's an obstacle, start for our start node, and destination for our destination node. We then get our obstacles from the user input. We choose a random row and a random column. Make sure that we don't already have an obstacle here, and then mark it blocked and increment our counter. We then get our starting cell from the user input, making sure that their input is valid, and then marking our start node in the array. We do the same for our destination cell. We make sure that the user input is valid, and then mark our destination node in the array. For the grass-fire discovery, this is a breadth-first search. We want to visit each of the neighbors and increment our counter, marking each cell with the distance from the destination node. So we start with our destination node, and we then make sure that the row and column we want to check is within the bounds of our array. If it is, we then check if it's the start node. If we found the start node, that's great, that we can finish our search because we found our goal. Otherwise, we can continue our search and append each of our neighbors to the queue to search next, incrementing our counter when we append it to the queue because it is 1 extra unit away in distance. Now for the actual pathing part of the algorithm, we take our distances that we found in the previous step, this time starting with the start node and traversing our grid with the closest neighbor each time. So we maintain a list called this path, which is the current path that we are testing to see if it leads to our destination node. This is a depth-first search, so we are maintaining this list by appending the row and column that we are visiting each time we go through. If we have found our destination node, we can append this path to our paths list. This paths list is the list of our solutions that lead to the destination node. We make sure that we're not trying to visit a blocked node because we can't travel through that. We then look for our smallest neighbor. We do that by checking the distance of this cell compared to the smallest distance that we've found for our neighbors. If we have found a new smallest distance, we can clear our smallest neighbors list and append this neighbor. Otherwise, if it is equal, we want to still search it because it is equal to the smallest distance, so we can simply append it. We then go through for each of our closest neighbors and continue this recursive search, each time continuing to visit our closest neighbors. Once we're done our search, we can go and print all possible paths that we have found, and then output the number of solutions we've found. Thank you for watching.